In this video, I'm going to talk about the equilibrium of rigid bodies as it relates to statics and future videos. What you should know before starting this is how the equilibrium of a particle works. So to start, we need to understand what a rigid body is. We knew that a particle was just a point in space, and it was pretty intuitive, right? A rigid body is not as intuitive. But a rigid body is actually just any structure that does not change shape as force is applied. Now, as you can see, I have drawn some examples of rigid bodies. So up here, we have just a beam, and there's a force being applied to it, and there's some supports holding it up, right? Here's another beam. It's fixed to the wall here. These are simply supported. Here. And what's down here? These are not beams, right? As you can see, we have forces being applied to it, but the shape is still the same. So they're rigid bodies, and this is called a truss. And it may look familiar because it is, you might say, oh, that's what bridges are made out of. Well, this actually is what a lot of structures are made out of. And we are going to learn more about that in the future. And this is called a frame. And what's the difference between a frame, truss, and a beam? Well, to identify this, when you see truss, think bridge, right? When you see frame, think motorcycle chassis, or the way a pedaled bike is built. And when you see beam, think of the big wood beams in your house that are keeping it upright, and the big wood beams that are keeping massive buildings supported as well. So what is a deformable body? Well, a deformable body is something that changes shape as force is applied. And there's not really many examples I can give you. Basically, everything changes shape as force is applied, but in physics, we like to think of like ideal cases here. And stuff like beams and trusses and frames are designed in a way that they don't change shape as much. And they don't change shape to a significant amount where we can call them deformable bodies in real life, of course. So knowing the difference between a particle, rigid body, and deformable body, we can go into the equilibrium of a rigid body now. So basically, the equilibrium of a rigid body is when you're given a rigid body and it does not change. The forces in the x direction equal to 0, and the sum of the forces in the y direction equal to 0, and so the total force on the object is also equal to 0. All of the forces basically cancel out and it doesn't move. But that doesn't mean there isn't anything acting on it, right? So as you can see in this example, we're given some beams that's simply supported. We have a force here acting in one direction, and in the opposite direction, we have a force here. And we also have to account for any force moments as well. So to solve these type of problems, we need to use the equilibrium equations, right? The sum of fx is equal to 0. The sum of fy is equal to 0. And we need to now take the sum of the moments as well is equal to 0. And of course, we need to specify which direction is positive and which direction is negative. So basically, you do this for the entire beam, and you solve for missing forces on the beam. That's a very simple way of putting it. First, we have to figure out, okay, what is a moment really? And then we have to figure out how these supports affect our structure here, right? Because what if I supported the beam differently? What if I decided to put, okay, you know what? We decide to put this simple support here again, but underneath it, I'm just going to put some wheels. Now that I have wheels under there, it has different degrees of freedom, right? It can roll this way and it could roll that way. Before, our beam couldn't roll at all. Like on this side, it can't roll, but what can it do? It can deflect, right? It can bend. So these, what supports you put on will affect the forces on the beam, right? Each support has a reaction force. And we're going to go over that in the next video. So before we do that, I want to cover what a force moment is. So before we get into reaction forces and supports and solving these problems that have to do with beams, trusses, and frames, I want to describe what a force moment is, because it will be in all of our future problems. So basically, a moment of a force occurs when a force is applied to a body and it gives it a tendency to rotate about a point. So let's use a door as an example, right? And let's look at it from like a bird's eye view, right? This is the top of the door. So basically, we have a body here, and it can rotate because it's on a hinge, right? It's on a door hinge. So our door can rotate like this or back this way, right? So let's call this point A. Remember, a moment is produced when a force is applied and our body here has a tendency to rotate about a point, and that point would be the door hinge, and let's define it as A. So if the door hinge has length D, and we apply a force right here called F, it produces a moment about A. And that moment is defined as the force multiplied by the perpendicular distance. Now, why is that important? Why is the perpendicular distance important? Well, let's do some test runs on how we can open this door, right? Where is the easiest place to open the door? Where do I have to push to have to apply the least amount of force to open this door? If you said the end, right where our force is currently located, you would be correct, because our force moment is greater. Remember, this is the tendency for the body to rotate. So as this increases, our tendency for our body to rotate is increasing. So to apply we want to apply the least amount of force to open the door, we would push it at the end. Now, how do we make our lives really difficult? How do we make our lives much harder? By pushing on the door very close to the hinge, right? Because then you have to use a lot of force, and you'd probably have to push it at a different angle. Like, it would just be really hard to open the door from that side, and you could actually just like break the door because you're just pushing on it, right? It does not want to open from there. The tendency to rotate is really low. You'd have to apply like a crazy amount of force. And why is perpendicular distance important, right? This distance along this door is where we are applying the force, right? And that is perpendicular to the point A. What if I applied a force right here? Now, you were probably not thinking that because it doesn't make any sense to open a door from, I don't know, the wrong side. Like, nothing's going to happen, right? You're just going to end up pushing on the door, and there's going to be zero rotation, zero tendency to rotate. So that little blue line I drew there is called the line of action, and that is directly in line with our point, right? And our other force was perpendicular to this line of action. And that's the force we can use to find the moment, because what if we put a force in line with the line of action? There'd be no rotation, right? And that's why we have to use the perpendicular distance and not a force directly in line with it. You can't use the horizontal distance. I'm going to call it the horizontal distance, but you can't use forces that go along the moment's line of action to find the moment, because it will always be zero, because it has zero tendency to rotate. And you can also think about a wrench trying to turn a wrench. You don't push on the handle of the wrench to turn it moment it's zero, right? You would go perpendicular from the point of interest and push it, and your tendency to rotate would be greater than zero, and you would be turning the wrench, right? So in summary, we covered that the equilibrium of a rigid body is pretty much the same as a particle, whereas we're dealing with something that has forces being applied to it in equal and opposite directions, right? We use something called the equilibrium equations, where it says that the sum of x forces is equal to zero and the sum of y forces are equal to zero as well. And that's how we solve these type of problems. We also talked about how there could be moments applied to these beams, trusses, and frames as well that produce a tendency for our body to rotate. Remember, it's not changing shape, it's just rotating. And we also say that the sum of the moments are equal to zero on a rigid body in equilibrium, right? Yeah, and we said a moment was defined as the force multiplied by the perpendicular distance to the point of interest. And that point of interest, it creates a line of action, right? And the line of action is going to be always perpendicular to our forces applied. And if you apply a force along the line of action, our moment is equal to zero. So when is our moment equal to zero? When force is applied along the line of action. And that's all I wanted to cover before we go into how these supports we have holding up our beams affect our problems. I am also going to talk about distributive loadings, and then after that we are going to dive into an example on how to solve these problems and solve for these forces. Thank you for watching. If you found this helpful, subscribe. And if you hated it, don't. Just drop me a comment, give me some constructive criticism on how to make these videos better. Have a great rest of your day. Thank you for watching.